Okay, English good to correct.
I got the multiple choice, by the way.
Well, Jawan's going to be 10 minutes late.
Okay.
That's assumed. So, the only people we're really waiting on are Emily, Luke, and Zach.
I think we should
We don't
do
Brandon go do the evaluation. She hasn't done it yet.
Favorite ones in late.
Wait, what? Of course she did. After she had tried to make sure we all
after
she had sent out that
Facebook message and said
Oh, I saw that message. She hadn't done it?
She left just a minute ago to go do it.
I got an email from her.
Yeah, she sent that email to everybody.
Yeah, she sent me a text, and I was like, I already did.
She sent email, text, and Facebook messages.
Oh my God.
I didn't do it.
Thank you.
Unbelievable.
Nice.
She does it really sharp. Did you guys do the evaluation?
Yes.
You're doing it right now.
Only you and Camille and not Buddy.
I've done it.
Oh, only Camille.
I'm the first person to do it. All right, good for you.
Ooh, now you know.
Yeah, Camille
That's lit.
a text.
This was like the first thing.
Facebook text.
Good, nice job.
It's almost a
Professional.
All right, so before we begin on this, Mr. Vestal was going to demonstrate the gravity assist using the interactive physics program.
Set that up pretty fast. Yeah, so always slow that down. So here what happens, you can see you can see it. As this thing moves this way, it's going to speed up as it approaches the larger body. Approaches the larger body, and then speed off that way. And if this body was stationary, then really the speed gain would be equal to the speed loss as it tries to fly away. But since they're moving further apart, then as this body slows down due to escaping gravity, then they just get further apart. So it ends up being that this one is able to steal velocity from this one. So let's see that again. Whoosh, that goes off.
So it does slow down the bigger body a little bit. You can see it's just before it goes off the edge there, it's at 1.996. Start off at 2, something like that. So it slows down a little bit. So how about if you think of this as a binary collision in 2 dimensions?
Then you can think of how, similarly, the smaller body, the two would collide, and the smaller body would end up taking impetus. The bigger body would impart impetus on the smaller body, so the bigger body would lose speed, and the smaller body would gain speed.
If we have an example, if they're head on and they bounce instead of using gravity, they bounce off of each other. This one, the smaller one, we're headed in here and bounce off of this one. What kind of velocity would it have after the bounce? Say it again?
The negative kind.
Yeah, the negative kind. She's ready for the end of the term. So we've done this collision with a binary collision where the target, the incident, well, one of the particles is much more massive than the other, right? And would have a lot of velocity coming out, right? So this is similar to an elastic collision. So is momentum conserved in this?
Yes.
Yes, at all times. How about kinetic energy? Is it conserved?
No.
Good. Why not?
Because...
Put it a different way.
Great question.
Is total energy conserved?
Yes.
And there's a change in the potential energy because the bodies are changing distance from each other. So therefore there's a change in kinetic energy. But if we consider them far enough removed, if this one starts far enough away, then the potential energy is almost zero. And And then if we wait until it gets past it and it gets far enough away, then the potential energy change will have been almost zero. And so it will be almost like an elastic collision in that case. So you could apply the same analysis we did before on this problem. Okay, good. Thank you. You got all dressed up for that. Let's see, this one is the same. Did you look at these other ones too? There's a couple of more, but you have to find them. I don't know how to find them. I forget how to do it. There they are.
Oh,
okay.
Is that like Orion's belt?
That's farther away, so now let's zoom in some.
Must be Orion's belt. There's 3 dots.
3 dots.
I could have said a small dipper, but he's just looking at like a big of a triangle.
Purely curious that time.
Okay, starting it from farther away here. There he is. Way out there.
Dang, it's coming.
Oh, that one's speeding up too.
Wait, can't find it.
Oh, there it goes.
Here it goes.
Oh, wait. Oh, it's turning.
And notice it's departing with a much increased velocity. Much bigger velocity than it had before. Stop. Okay. And
Yeah, I was about to say, it's like the slingshot thing.
here's one where, let's see.
What the heck?
Better reset this. Try again. Okay, so that's a bigger angle. Did you catch that one? Goes by quick. Reset. It's easy to lose this thing because the magnification is so tricky. Try again. Okay, it's coming from below and zings off. Not much change in angle, so it doesn't get much of a boost. It has to really go around it in order to get a big boost. Okay, good. So let's go on to any questions. Go on to the, God bless, to the final. Any questions about the time for the final? Everybody know Wednesday evening, Friday afternoon?
Oh, Wednesday evening?
Yes, sir.
Oh, thank you.
And both of those instances, it'll be in this room, right?
Yes, sir.
All right.
Oh, it's in this room too?
Yes.
Oh, yes. I like that.
Did you say whether you were planning on being here at all next week, other than that?
I haven't heard anything. I was wondering to hear.
This, actually.
Okay, we talked about this. Should we decide Tuesday? What's a good
You
day?
decided Tuesday.
Tuesday works for you.
Y'all are welcome to meet anytime you like. But I do have a schedule.
Well, we were talking about doing something on Tuesday, so if you
That
could
was
make it
good.
Tuesday, that would probably be preferable.
Okay, what
If-
time? What time?
We didn't get that far.
Morning?
Whatever time works for
I
you.
think
Yeah.
Tuesday.
Whatever time.
Oh,
Maybe
8 to 8.
Miss Swanson has a very quiet
Hey, yo,
voice.
Shelby!
You have to use somebody.
Dang,
Does anyone have a Tuesday exam? Because if not, then we have all day to do it.
I have
Like,
something I have to go to at 9 a.m.
I have kids that get out of school at 2:30 on Tuesday that I'd like to be home for, so.
so like, those are the only
Midday
constraints.
would probably be
Like,
best.
should we do it fairly
Like early
Tuesday?
midday?
Like 11?
Yeah.
Yeah, that's
10 or
okay.
11, yeah.
Yeah.
I should be out of that in 2 hours, hopefully.
Is that your appointment?
My appointment starts at 9, so it should be not bad.
All right. I think 11 o'clock Tuesday works, I think.
Yeah, if not, just another time I will work with you.
Would somebody please send me an email
Let's go.
to remind me 11 o'clock on Tuesday, okay? I think that works, but I don't have my calendar with me, but I think it's okay. Okay. There were only 3 people that I know of coming Wednesday. Mr. Covington, Mr. Vestal, and Ms. Swanson. Anybody else coming Wednesday? So we got a couple people who aren't here. They may show up. You just even it out?
Yeah.
Okay.
I ain't trying to leave. I ain't trying to stay at the chem exam.
Take it on Wednesday, be done.
If it was Wednesday,
Take it on Friday, study more.
There.
Okay, so we were working on number 5. starts getting into the imperiometric section. We have this. Let's see. We didn't do this one? Is that right? I did not do this one yet. We started to set it up and I didn't finish it. Is that correct?
Correct.
Yes.
Yeah, we got him to number 4.
How do you know what the weight of the system is? Like,
Okay. And you're given the pulley consists of a solid disk of uniform density, so you can refer to the table of moments of inertia that you will be provided and determine that the moment of inertia is 1/2 mr squared for that. Okay, and then you're defined the linear and angular accelerations and tensions in the rope. There are possibly 2 different tensions here. So let's draw a force diagram. Call that T1. Let's call this, that's little m, right? G. And I'm going to choose my coordinate system so that y is pointing downward. And the force is acting on this one. The force of the rope that's hanging down from the ceiling. There's gravity. Then there's also the tension from the other rope that connects to the mast that's dangling from the rope. Okay, so 3 forces present on this. And we want to define also an angle here. And I choose to make it clockwise because when this pulley is turning clockwise, then the mass is going down in positive y, so that these are consistent. Increasing theta is in the same direction as increasing y, right? That's what I want to have happen here. Otherwise, you get this negative sign that floats around for a little while. It's not a problem. You just have to be careful. As long as you're consistent, you could do it. Choose the coordinate. For example, y could have been up, or theta could have been counterclockwise. Doesn't matter. As long as you're consistent, it will all work out. Okay, we have 2 bodies then, 2 equations of motion. Now, you want to note that I'm choosing the coordinate system for the rotating body at the origin there, at the center of the wheel. So the torques due to T2 and mg both vanish because the lever arm equals 0. Has no length of lever arm. Something acting on the center there cannot produce torque. Distance from the center to the center is 0. So the lever arm is 0. So the only force that produces a torque is that second rope, the one that's hanging down to the mass. So we have these 2 equations, and we need to add a third, which is the connection of the fact that the rope that's playing out is also the rope that turns the pulley. And so y is equal to r theta is the no-slip condition for the rope. Okay, and it's also an ideal rope in that it's massless and stretchless. So it's stretchless means that the tension is the same on both ends, and also massless means the same thing, right? We're not writing an equation of motion for the rope itself. We're considering the rope just to be a massless thing that connects the pulley to the mast that's hanging down. Okay, and we could also write this in terms of the accelerations there. So if we set A equals to y double dot, then we have A is equal to G minus T1 over M, and 1/2 M R squared alpha is equal to R T1, and A is equal to R alpha. I'll just keep the mass here, make it a little bit easier. Don't necessarily want to pull the mass out yet. Okay. So, 3 equations.
let's write down the unknowns. A alpha T1. Notice that T2 has not appeared in the equation of motion for the rotation of the pulley, and that's because there is no torque that produces. We also could write an equation that represents the equilibrium of the pulley. That is, the pulley is not accelerating up or down, and that would say that T2 is equal to T1 minus T1 plus mg. So we could write an additional equation. T2 is equal to T1 plus mg, and this would be due to the pulley is in equilibrium, translational equilibrium. It's not accelerating up or down. Okay, so we have these 3 equations and 3 unknowns, and it's a matter of applying algebra. Do you want me to go through that? Okay. So let's look at. I have 3 equations and 3 unknowns. All 3 are linear equations, so this is just a straightforward way to do this is to simply eliminate variables one at a time. So the simplest one to begin with is the third one. We can eliminate, say, alpha in terms of A. So wherever alpha occurs in the second equation, I'm going to put it in terms of A. So now I have 2 equations. Then I reduce 3 equations down to 2, and I have also eliminated one of the variables. Okay, so I put, in place of alpha, I put A over R, and then that cancels one of the R's. Okay, everybody okay on how I did that? So that gives me 2 equations and 2 unknowns, so my unknowns now are A and T1. And now I want to eliminate another one. Again, I choose one of them to eliminate. So let's suppose I eliminate T1 in favor of A. So it's going to be 1/2 MA. Okay, so then I can substitute T into the equation. The one remaining equation, and I have an unknown A. Then I solve for A, so it's 1/2 M plus little m times A equals little mg, so A is equal to M over little m over little m plus 1/2 big M times G. Or I could pretty it up a little bit like this. I don't like the 1/2 there, either way. Good time to check for dimensions. This should be an acceleration. I have a ratio of masses here, so this is in fact dimensionless. And so A and G both have dimensions of acceleration, so that should be good. Okay, now I can work my way back up. I have got A here. Now I can go back and get T1. T1 is 1/2 MA, and A is going to be M over M plus 1/2 M times G. So this looks like M over 2M plus MG. That's T1. And then I can find alpha also is A over R. Okay, so there I have the 2 accelerations and the tension in the rope. And then finally, to find the other tension, T2, I add mg to T1. And I can do a little simplification here if I have time. This is T2. Okay. So, main thing is to keep your widths about you. Keep writing down what are the unknowns. And you might want to write down the things that are known. The things that are known are the things that we're given in the masses here. We're given the mass, the two masses, the radius, and the acceleration due to gravity. So the unknowns should be written in terms of those known things when we're done. And so that's in fact what happens here. We've got the acceleration, the tensions, all in terms of those masses and the acceleration due to gravity. Any questions? Okay. So, seems like these are classic problems that you see on a lot of tests. They test a lot of different things, setting up the coordinate system, recognizing the forces involved, calculating torques, writing down appropriate equations of motion, and putting in constraints and solving. Got a few steps. Lots of things to practice in all of those steps. Okay, number 6 is a block sliding up an incline ramp, given an initial velocity v, comes to rest at distance d. So the question is, how far does it go before it stops? Calculate d. So you know the acceleration due to gravity, you know the angle of the incline, you know the mass of the body. And also you're told that there is friction. So sandpaper, if you want to exaggerate it some, let's take a case with a lot of friction, some kind of sandpaper here. Okay. So again, start with a force diagram. What are the forces acting on this body?
Force of gravity. Normal force.
And kinetic friction. Right. And that's it. Okay. And then let's define a coordinate system. There's equilibrium in the y direction. Means it does not accelerate. So that means there's no net force in the y direction, and so the normal force balances the amount of the component of gravity perpendicular to the ramp. So that's the magnitude of the normal force. How about the force of friction? In magnitude, it's mu k n.
Dr. Bell?
Yes, sir.
But we need to give the reasoning why we don't show the y direction, or can we just have it understood?
Why I didn't show the y direction?
On the test, do we need to show why we're not bothering with y? Do we need to show that equals 0 also?
Equilibrium in y. It said equilibrium. That's the reason. It's not accelerating perpendicular to the ramp. That's the reason. You mean why I didn't write down my double dot is equal to 0?
He's asking if we need to write that on the test.
I want reasons like this.
Okay.
Yeah. Now, the normal force is equal to mg cosine theta because it's at equilibrium in the y direction. Yep. I want reasons. Don't just throw equations at me. Okay, so now then we have in the x direction, the equation of motion is going to be minus mg sine theta minus mu k mg cosine theta. Both forces work to remove impetus, remove upward impetus from the body. Mass cancels, so the acceleration then in the x direction would be minus g times sine theta plus mu k cosine theta, but you weren't asked to find the acceleration, right? But that's what it would be. Instead, you want the work done by each of the forces while the box slides a distance d up the ramp. So how many forces are present? There are 3. So we need to compute the work done by each. Work done by the normal force, work done by gravity, work done by the kinetic friction. What's the work done by the normal force? It's 0. Why?
Because the distance is 0.
No. Oh, the distance in y. Yes, correct. Yes, the distance in the y direction is 0. Thank you. That's fine. In other words, it slides perpendicular to the normal force So it slides perpendicular to n. And another way of saying that is that there's no motion in the y direction, which is the direction of n. Gravity is then the work done by gravity. It's negative mg d sine theta. And notice that it's negative because it's in opposite direction. The force opposes the motion. Work done is negative. And the work done by friction is minus mu k mg cosine theta. And then I need a distance as well, so I'm going to put d in there. So both gravity and kinetic friction do negative work. And applying the work energy theorem, the change in kinetic energy is equal to the work done. In this case, the work is negative, so the kinetic energy is lost. So delta K is K final minus K initial. The final is 0 because it comes to rest. That's what we're looking at, the final being the point when it's at rest. And the initial kinetic energy is 1/2 mv squared. Okay, so that means then 1/2 mv squared is equal to mgd sine theta plus mu k cosine theta, equating the amount of kinetic energy that's been lost to how much work was done against those forces. The mass cancels out because all the forces are proportional to the mass, all the ones doing work. And so the distance then is v squared over 2g times sine theta plus mu k cosine theta. That's how far it travels up the ramp before it stops. By equating the amount of work done by both gravity and friction to the amount of kinetic energy that is lost. It loses all of its kinetic energy. Okay, you could try a few things. Dimensional analysis here. This should be a link. So we have a velocity squared over an acceleration. The angles and the coefficients of friction are all 0, so you can check the dimensions there. The velocity squared over an acceleration is in fact the distance. You could check a few common sense things. So a couple of easy things would be put the ramp down, make it horizontal. And then gravity is doing no work. It's all kinetic friction at that point. And the kinetic friction would be just the normal force, mg, times mu k. So the normal force, the kinetic friction is just mu k mg. And so in that case, it would just, the sine of theta would go to 0, and you just get v squared over 2g mu k. You can check to see if that one works. Simple case. Any questions? Okay, again, keep an eye on what is known and what is not known. The knowns are the mass, the velocity, the acceleration due to gravity, the coefficient of kinetic friction. And the unknown, in this case, is just the distance. So you're expressing the distance in terms, and there's an angle in here as well, incline of the ramp. Okay? Any questions? Okay, you should be able to invent variations on these problems yourself. Right? It should be pretty easy to do. Come up with simple variations. That block could have been sliding down the ramp. Is it going to stop? Things like that. If it starts off at rest and the incline is enough that static friction is not going to keep it still, then what's the velocity at the bottom of the ramp? It's a similar sort of problem. Okay, on to the binary collision. Masses are the same. And you're given 3 cases, A, B, and C. So the second body is at rest. Case A is the perfectly inelastic collision. That means they stick, the after is like this, and the velocity afterwards, they stick, move together. So in an inelastic collision, in all binary collisions, the momentum is conserved. So the collision before is mv, the collision after is 2 mv prime, and that implies that v prime is equal to v over 2 in an inelastic collision. Now, what is delta k? Asking for delta k over k initial. How much is lost divided by the initial? So the k initial is 1/2 mv squared. K final, and be a little careful here, it's 1/2 times the mass of the body, which is 2 times the mass of the first body, times v prime squared, the mass, the velocity, the square of the velocity of the combined composite body. So when all is said and done, the kinetic energy is reduced to 1/4 of mv squared. So the change in kinetic energy is minus 1/4 mv squared. It loses 1/4. And that fraction is then minus 1/2. It goes from 1/2 down to 1/4, so it loses 1/2, loses 50% of its kinetic energy in that case. So that's case A, was the inelastic collision. Let's look at the next case was the elastic collision. In the elastic collision, both momentum and kinetic energy are conserved. That's what we mean by an elastic collision. And so the after picture, the two bodies are traveling separately. Now I'm going to draw the two velocities to the right because a positive velocity is to the right. I've chosen that to be, so I'm going to draw them that way. I don't know exactly without having worked it out. One of them might be moving to the left. It's entirely possible. For equal masses, that won't turn out to be the case, but it can happen if the masses are not the same. Okay, so delta P is 0. So I write down A. Delta K is 0. Same mass again in both cases. So the masses drop out and the factors of 1/2 drop out. Let's call this B. Two equations here. Now it's a little bit trickier, this part. This is where it takes a little bit more work. And keeping your wits about you. What are the unknowns? V1 prime and V2 prime are the unknowns. You want to know what the velocities are after the collision. And the one known is just the initial velocity. All the masses have dropped out. So the only part, the mass is part of the problem, but it turns out that in these equations it's dropped out. We have two equations, but one of them is quadratic, and so this is not quite as easy as the previous, the Atwood machine or the modified pulley machine, where the equations were all linear. So now we have to be a little bit careful about what we want to do. Okay, and notice that we want a solution where V2 prime is not equal to 0, right? V2 prime. We don't want V2 prime to be 0 because that would be the same thing as if it's not moving. The target, there hasn't been a collision, in other words. So we're looking for a solution where V2 prime is not 0. Okay, so let's solve for V2 prime, both A and B. Put the V2 prime on the same side. I'm rewriting those two equations. And then I'm going to divide one by the other. Now I can do that because I said V2 prime is not 0. So I can divide by V2 prime. That you have to be careful about, that you haven't somehow assumed something that might not be true. Okay, so on the left-hand side, the V2 prime squared divided by V2 prime gives just V2 prime. And this we have the construction of difference of squares divided by the difference is going to be the sum. So this is V plus V1 prime. Okay, let's call this equation C. It's been derived from B and A, but I can still use A with it. Now I have two equations and two unknowns, but they're linear. And I've excluded the possibility that V2 prime is 0. Okay, so then I could say V2 prime minus V is equal to V1 prime, and V minus V2 prime is equal to V1 prime. And that means immediately that V1 prime must be equal to 0 because it's equal to its own negative. And having determined that, I know then that V2 prime is equal to V. Another way to solve this is to solve for, say, V2 prime or V1 prime in A and substitute into the quadratic in B, and then you have a quadratic equation. You just apply the quadratic formula. You get two solutions. One of the solutions will be this one. The other solution will be V1 prime is equal to V and V2 prime is equal to 0, which is the one that we excluded up here when we divided by V2 prime. But that would be the other solution that would come out from the quadratic. This also solves the condition of no change in momentum and no change in kinetic energy. Okay, that amounts to no collision, which certainly would satisfy no change in momentum and no change in kinetic energy because nothing is happening. But that's not the one we're looking for. We're looking for the one where there has been a collision, something has changed, and so that's that one. Okay, now the last part of this question is, what is delta K? Well, 0. It doesn't lose any kinetic energy in the last equation. Okay, case C. You're told that V2 prime is 3/4 of the initial velocity. So what is, I'm sorry, that's V2 prime. What is V1 prime then? Well, you know that the total momentum is conserved. Let's drop the masses. Therefore, the two velocities at the end have to sum up to be V, and so therefore V1 prime is going to be 1/4 of the velocity. That's the only way that momentum will be conserved. Now we need to calculate the change in kinetic energy over the initial. The initial, of course, is 1/2 mv squared. And be careful of the final. Get all the bodies in it. There are two bodies moving. There's the first body and then the second body. They're both moving. The first body has 1/4 of its initial velocity speed, and the second one has 3/4 of the initial speed of the other one. So then I need to simplify this. So it's 1/2 mv squared, and I have 1/16 plus 9/16, so that's 10/16, or 5/16 mv squared. Is that right?
Yeah.
I think it's right. 16. Okay. So the loss in kinetic energy goes from 8/16 down to 5/16, so it loses 3/16. And And then if we divide by the initial kinetic energy, this is 1/2 mv squared. If I've done all this correctly, it's lost 3/8 of its initial kinetic. It's lost 3/8 of initial kinetic energy. So not quite half, but certainly more than 0. Half. Remember the inelastic, it lost half, and the elastic it lost none. So I guess you could say by this it's a little closer to inelastic than elastic, but it's in between.
Like a 37.5%.
Okay. All right. Questions about that? Again, that's the hardest part is that section B, the algebra. You should practice so that you can get that down really good. And again, it's just a lot of this is just algebra, keeping track of the knowns and unknowns and how to rearrange the equations, how to solve, to eliminate variables, and substitute back in. Then the rest of it is keeping track of what it is that you're supposed to be doing overall with this problem. Okay, number 8. Consider some property whose measure is c, which is a function of time. You're given the equation of motion. Alpha c double dot is minus beta c. Now notice this is both sides are functions of time. This is true for all time.
What's that Greek letter called again?
Xi.
What?
Xi.
Okay.
It's not epsilon. That's not
No, it's
epsilon.
not.
That's not epsilon. This would be epsilon.
No, epsilon's the cool one.
No, sigma.
No.
Upsilon is also a Y.
Yeah, upsilon.
Phi
I can't draw upsilon very well.
Alpha.
So
We call it upsilon.
the point, of course, is that the symbol itself is unimportant. What we have is an equation that looks like something, right? Looks like the simple harmonic oscillator. You should recognize this as the simple harmonic oscillator. In that, there's something that looks like an acceleration on the left-hand side and then something that looks like a linear restoring force on the right-hand side. So it's like a simple harmonic oscillator. Okay, so you're given that, and you're given also the initial conditions. The initial value of c, and you're also told that it starts from rest. It starts off with no change. Okay, so direct substitution then. By direct substitution, you are to substitute this equation. Try this solution out. Does it work? So we have 3 unknowns. A, omega, and delta. Those are unknowns in that solution. And you're supposed to find out what you can about those 3 by substituting them into those 3 equations, 2 of which are only at the beginning, just initial conditions. That first equation there is for all time, not just initial time. Okay, so in order to do those substitutions, let's evaluate it at 0, for example. This is a times cosine of delta. Let's take the derivative. Oops, I need an omega. And then that's for any time. Then at time 0, it's going to be minus omega a times sine of delta. And then let's take another derivative, minus omega squared a cosine omega t plus delta. Okay, now I've done all that work, I can go back up and substitute all of these into those equations. So let's go and do the substitution. This is the direct substitution part. So that first equation, which is the equation of motion, would be alpha times, not minus alpha, but alpha times c double dot. That's the left-hand side here. That's alpha times c double dot. And that's going to equal minus beta times c, which is a cosine omega t plus delta. See what I'm doing? Everywhere there's a c or a derivative of c or whatever, I'm going to substitute that one in. So that's the first equation. The second equation is going to be a cosine of delta is equal to, oops, I'm carried away with my wiggles. And then the third one is minus omega a sine delta is is equal to 0. Okay, so now I've done the substitution, and now it remains to figure out what values of A, omega, and delta will satisfy these equations. So the easiest one to begin with is the last one. We don't want a solution where A is equal to 0 because that would mean C is equal to 0 for all time. So that's not one that's going to be very interesting. Yes, sir?
Where did the negative alpha come from?
Because the C double dot right here has a negative in it. And I multiply it by alpha. Alpha times C double dot. And C double dot has a negative sign.
Oh,
because that
alpha time. Okay, yeah. All right.
Okay, so let's look at that first one there. A is not 0 because then it would be impossible to satisfy the second equation where A times cosine of delta is something not 0. If A were 0, it wouldn't be possible to satisfy the second equation. So I know A is not 0, and omega can't be 0 either. So that leaves me with sine of delta is equal to 0, which implies that delta is equal to 0 or delta is equal to pi. That's a possibility, that delta is pi. So let's try delta equals to 0. We go up to those first two equations and we put in delta is equal to 0, especially that second equation. Let's look at that second equation. If delta is 0, the second equation becomes A times cosine of 0 is equal to C0, and cosine of 0 is 1, and A would equal C0. So delta of 0 goes with that one. Or if delta is pi, then cosine of pi, A times cosine of pi is C, and this is negative 1, and so that would mean A is minus 6C. So I could have either of these. I'm happy if you figured out only one of them. There are two possibilities there. You're asked to find some conditions, some values of these variables that will satisfy the conditions. You don't have to find all of them. Okay, so now we go back to the very top equation, the first one there, which is the differential equation, and we know we're given A, and so we have minus alpha omega squared A cosine omega t. We know A is, we know what A is. A is 6C or whatever. And let's suppose we take delta as 0. Then A is 6C naught. And then this is minus B times A cosine omega t, where A is equal to C naught. So we can substitute that into there. But it doesn't matter because we can cancel it. Now, the left-hand side is a function of time. It's a cosine. And it has a certain amplitude. The right-hand side is also a function of time. It's also a cosine, and it has the same frequency. So those two sides can be equal to each other if the amplitudes are the same. And that means then that A alpha times omega squared must equal to beta. Or in other words, omega is square root of beta over alpha. Which is like what we got in the simple harmonic oscillator, where beta was K, alpha was the mass, the frequency is square root. So if you have an equation like this, then the frequency, it admits a periodic solution with that frequency, where beta is whatever, and alpha is whatever. You just take the ratio and the square root of that gives you the frequency of the motion, whatever those are. Okay, so this is an example of simple harmonic oscillator and direct substitution. Okay, good exercise in direct substitution. Number 9 is pretty quick. Don't make it hard. If I have a planet of mass m, radius r, and I'm going to put another body of mass little m right above the surface, what is the force acting on, due to gravity, acting on that little mass? Newton's law of gravitation says the magnitude of the force is going to be g times the product of the masses divided by the square of the distance from the center of the planet, which is the radius because you're on the surface. And Newton's law says then that this force is equal to the mass times the acceleration of that test body, so we can cancel the masses, and the acceleration is just the product of that gravitational constant, universal gravitational constant, big G, times the mass of the planet divided by the square root of the radius. For the Earth, we plug in the mass of the Earth and the radius of the Earth, we should get little g, which is 9.8 meters per second squared. Yes, sir?
For any planetary equation like this, are you going to give us those constants like mass of Earth, mass of the Moon, stuff like that?
Say it again?
Like the mass of the Earth, mass of the Moon, radius of the Earth.
If I wanted you to figure it out, yeah. Yeah, generally speaking, I don't expect you to know big G. I don't know big G. I should know big G. I don't know.
6, 7 times 10 negative.
Oh, all right.
We use it so much that it's ingrained into us. Like,
Big G? Big G? You have big G and brain?
We need to know it per mass form.
Little g and brain.
Okay.
oh my gosh.
All right, any questions? Don't make this one too hard. This is an easy one. It's only 5 points. This is supposed to be just a quick and easy thing. Right? Just to make sure you understand what the significance is of all these symbols. Okay, but I have to find some way of working Chapter 8 into the test without making it too complicated. Right?
What's Chapter 8?
Gravity.
Do we have polar?
Huh?
Do we have polar? Do we have to take
have
north
polar
and south
coordinates.
poles and we make polar? Do we have polar equations?
Polar
Don't
equation?
answer that question.
Polar stuff.
Polar.
Oh, coordinates. That's good.
Polar coordinates.
Yeah.
Oh, polar coordinates. Yes, that will be on something having to do with polar coordinates is certainly fair game for the test. So let me sketch the solution for the last one here. It's a rod of length L. The mass is uniform all the way down, right? And so I want to write down the equation of motion for this thing. What kind of motion is it? It's rotation. It rotates, swings back and forth. So I want to choose a coordinate, an origin for my coordinate system. And the natural place is at the hinge, because that's the point that's rotating around. And you see that there's a good a benefit from doing that. Let's look at the force diagram. The gravity acts on the center of mass, which is halfway down the rod. There's another force, which is the force due to the hinge, and that changes as it swings. And it's a little hard to figure out. Not real hard. Actually, you can do it. But it's not something, you can't just state what the force of the hinge is. It depends where it is in its swing. It's changing with time as it goes through that swinging. But the torque due to the hinge is 0 because I've chosen the coordinate system at that point. So I don't actually have to figure out what it is. The torque due to gravity is going to be the lever arm, which is L over 2, right? This distance is L over 2, times mg times sine of the angle between the two directions. And then I want a negative sign if I'm going to have theta positive as I do this way. So I want the torque is going to be negative because it's trying to make it come back around, make it swing down.